Station 3. I've got a balance beam here, and I've got 100 grams here, so that's a 1 Newton weight, 1 Newton force, and here that's 10 grams, so that's a 0.1 Newton force. And that distance there is 50 centimetres, and this distance here is 5 centimetres. So this force is 10 times further from the pivot here compared to that force. And that's the reason why it's almost perfectly balanced at the moment. So I don't really need to apply any additional force to make it turn. It will just turn very easily on its own. You can do lots of calculations using moments, the turning effect of a force, but that's not what this one is about. Here I'm thinking about the size of the force and the distance that it's moved. Because if you remember from Station 2, if you move a 1 Newton force through 1 metre, then you've done 1 joule of work. There's been 1 joule of energy transferred. So what's going on here? I'm going to start with the balance beam in this position, so the 0.1 Newton force, or sorry, the 10 gram mass is just sitting on the table there. And what I'm going to do is I'm going to measure how far that one moves down and how far this one moves up. Okay, so all I'm going to do is take it off the table and allow it to change its position so that this one is caught underneath the table. And this has moved down by 6 centimetres, and this one has moved up by, let's just get it back to its original position, so that is that's 0.6 centimetres, sort of. Right, so how does that work then? So this is 0.1 newtons. We'll just use it centimetres to start with, it's a little bit easier, and then we'll do it properly in joules. Right, so this is a 1 Newton force that's moved through 6 centimetres. So start that again. It's a 0.1 Newton force that's moved by 6 centimetres. 0.1 times 6 is 0.6. And over here I've got a 1 Newton force that's moved by 0.6 centimetres. So 1 times 0.6 is also 0.6. So 0.6 there, 0.6 here. If we do that properly using distance measurement of a unit of distance of metres, then this is a 0.1 Newton force that's moved by 0.06 metres. So that gives us 0.006 joules. You might have to write that down, mightn't you? And this one over here is a 1 Newton force that's moved by 0.6 centimetres, so that's 0.006 metres. 0.006 metres times 1 Newton is 0.006 joules. So 0.006 joules there, 0.006 joules there. And this is the most important rule about energy. Conservation of energy says that in any closed system, the total amount of energy at the end of a process must be equal to the total amount of energy at the beginning of the process. Or you might have heard that as energy cannot be created or destroyed. So if there's 0.006 joules of work being done at this end to move the beam, then we must see that as 0.006 joules of work that's done at this end to lift this load up. Okay, here's another example. This is using a pulley. So both of these would be examples of machines in physics. In physics, a machine is just something where you can use a smaller force, where you can apply a smaller force in order to do some work that requires a bigger force. So here the smaller force lifted the bigger force, moved the bigger force, and here with a pulley system we use a smaller force pulling on the end of the string to lift a bigger load over here. Okay, and I want to do the same thing. I want to think about the forces and the distances moved. So what I'm going to do is, first of all, let's do distance. Actually, let's do force while it's sitting there and it's ready. So this one is 1, 2, 3, 4, 5, 6. There's 600 grams there, so that's 6 newtons of weight. So a force of 6 newtons, and when I pull this up here, I get a force of about 2 newtons. Okay, so 6 newtons and 2 newtons. And then let's have a think about distance. So I'm going to hold my fingers at about the 40 centimetre mark on this half-metre rule, and I'm going to pull until my fingers are at the 10 centimetre mark. So I've moved by 30 centimetres. Yeah, I've pulled the string 30 centimetres. How far has the load moved? Well, it's moved 10 centimetres. It's gone from down there up to the 10 centimetre mark on the half-metre rule. Okay, so let's think about that calculation then. Have we got conservation of energy here? Well, I applied a force of 2 newtons and I moved it 30 centimetres. Just do it just using centimetres to start with to keep it easy, and then we'll do it in joules in a moment. So 2 newtons times 30 centimetres, so that's 60. And here I had a 6 newton load and I moved it through 10 centimetres, so 6 times 10 is also 60. If we want to do it properly in joules, we need to say a 2 newton force moved by 0.3 metres is 0.6 joules. And here we've got a 6 newton force moved by 0.1 metres, so again a 0.6 joules of energy transferred, of work done. So energy is conserved. Although I applied a smaller force here, I moved it through a bigger distance, and the force times the distance gives us the energy that I put in, and force times the distance for here is the energy that I got out, and those two things are the same because again there's very little loss to the thermal store of energy. Very little stuff's getting warm here because the friction in the pulleys is very small.